Deltec, Chem 100, Chem 110, Unit 2 continued, calorimetry, heat, and specific heat. So last time we talked about a calorimeter. It's used to measure the transfer of heat from some object. Could be food, it could be hot metal, it could be cold metal that's absorbing heat from the water, and heat is transferred between that object and water. And you measure the heat transferred to the water, or the loss of heat from the water, by knowing how many grams of water you have, a property of water, which is called specific heat, and the change in temperature in that water. So if we look at this diagram here, you have a very simple calorimeter. You can even make it from a styrofoam cup, from a coffee cup, and a thermometer. And you're just going to measure the heat being lost by an object, and it will be transferred to the water. So the heat lost by the object is exactly equal to the negative value of the heat gained by the water. So specific heat is the amount of heat needed to raise the temperature of an object, of a substance, that's exactly 1 gram of that substance by exactly 1 degree centigrade. Now that means the same thing as increasing it by 1 degree Kelvin, since those two are the same size degrees. So in other words, if a substance is hard to get the temperature up, in other words, you have to add a lot of heat, you have to put it under a fire for a long time to make it warm up to a higher temperature, that would be substance with a high specific heat. Substances like that would include water. Water is notoriously difficult to warm up. You have to add a lot of heat per gram of water per 1 degree you want to increase the temperature. Whereas metals like iron and even aluminum, they don't require nearly as much heat. They have low specific heats. The amount of heat, the amount of energy, joules or calories, per gram of that material per 1 degree is a smaller number. It doesn't require much heat to raise the temperature. So it's the heat per gram per degree, or the joules per gram per degree. And so a specific heat we abbreviate as C. Sometimes you'll see this abbreviated as SH in some first-year chemistry books, but the proper abbreviation is C. It comes from an other term referred to as heat capacity, which is related to specific heat. So heat is not the same as specific heat. Heat is the total energy you're adding. So it's equal to the specific heat, which is the heat per gram per degree, and then you have to correct it by how many grams you actually have by multiplying it by the mass, and you have to correct it by how much you really are changing the temperature by multiplying it by the actual change in temperature, because you're not usually taking 1 gram of material and you're not just looking at it increased by 1 degree. You're using a different number of grams, which you multiply by m, and a different change in temperature, so you multiply by the real temperature. And when you correct that, you end up with a formula, Q equals C times M times delta T. Delta T, anytime you see a delta, it means the change in something. And it could be the delta T, it could be delta heat, it could be delta velocity, depending on what subject you're studying. But a delta is always the final version of that number minus the initial. It always goes final minus initial to be a delta. It's always what you end with minus what you start with. So we have this equation, Q equals Cm delta T, or Q equals Cm times parentheses T final minus T initial. And the units of Q, heat, are in joules or in calories, and the units for the specific heat are calories or joules per gram per degree. And that's how you'd read that. It's per gram degree or per gram per degree. And you multiply it by how many grams, and you multiply it by how many degrees you really are changing, which is the change in temperature. Now, the specific heat of water is 1.000 calories per degree gram. And that may seem very odd that it's such a perfectly round number, because that was intentionally defined that way years ago. But that works out to 4.184 joules per degree gram, because remember, 4.184 joules equals 1 calorie, so that's why these look familiar. Now, that's the unit. Now, these numbers look small, but in fact, in specific heat terms, these are actually considered quite large. Metals typically have values around 0.2 to 0.6, some are as high as 0.8, but most of them are around 0.2. So you can see it's much harder to heat up water than it is to heat up metal by adding heat to raise its temperature. So be careful how you use the word heat. I should become more careful how I use it too, so I don't confuse you. So to solve this equation, all you need is everything but one of these values. So if I gave you the specific heat, the mass, and two temperatures, the before and after, you could figure out how much heat was necessary to raise that object by a certain temperature. So let's look at that. How many kilocalories, so now we're talking about a different unit of heat, are kilocalories of heat, Q, are absorbed when 85.0 grams of water are heated from 23.2 degrees Celsius to 61.5 degrees Celsius. The specific heat of water is 1 calorie per degree gram. So what do you have? You have the original formula. We have everything but the actual heat. We know the specific heat. It's 1 calorie per degree gram. We know the mass, 85.0 grams. And we know the before and after temperatures. The final is 61.5, and the initial is 23.2 degrees centigrade. We plug these in, and we get 3,255.5 calories. Now you'll notice the question asked for kilocalories, so you have to convert that to kilocalories first by dividing by 1,000, because remember, a kilocalorie is 1,000 times bigger than a calorie, so the number must be 1,000-fold less. So you just move the decimal place 3 spots, and you end up with 3.2555 kilocalories. But remember, we have to concern ourselves with sig figs, and you'll notice that 3 of the numbers up at the top have only 3 sig figs, therefore we round it to 3.26 kilocalories. How many joules is that? Well, we know that there are 4.184 kilojoules per kilocalorie, or 4.184 joules per calorie. So we multiply it by that, and we get 13.6 kilojoules. Here's another example, and I'll leave this for you, but here we have 62.66 grams of an unknown metal release 3,078 joules of heat energy. So you now have been told the mass and the energy, the heat, the Q, not the specific heat. And the temperature is observed to decrease from 96.7 to 31.6. So what you know right away is the heat that's released is negative. So don't forget to put a negative sign in there, because your actual heat, the Q, will be negative 3,078 joules, because it's released heat. It's not absorbed heat. So we'll start with the equation. You can solve for C because you're being asked for the specific heat, and then it's a matter of plugging in the numbers, and you end up with 0.755 joules per degree gram, which is a pretty typical number for a metal. If you wanted to convert that to calories per degree gram, again, you use that 4.184 conversion factor, only you have to put it on the bottom. It will convert, the joules will be canceled, the calories will replace the joules, and you'll end up with 0.180 calories per degree gram. Now, in a laboratory example, if you're actually doing an experiment, typically you're not looking at one object, you're looking at 2 objects. You're looking at, say, a metal that is hot, a hot piece of metal, and you're dropping it into cold water. And the metal will lose heat, so you have an equation for that, and the water will gain heat, so you have an equation for that. And you're missing some variables from each equation, so you have to use one equation to help you with the other equation. Now, we know the specific heat of water. The specific heat of water is 4.184 joules per degree gram. And we are told in this problem that we have a certain mass of an unknown metal that's initially 96.5 degrees C. The metal is dropped into 120.0 mils of water at room temperature, 21.4 in this case. So we have to turn the mils into grams first, knowing the density. Using the information we learned from the last unit 1, we've learned how to calculate grams if we know the volume and the density. The final temperature of the water is 29.7 degrees C. What is the specific heat of the unknown metal? Well, one thing we have to remember is This is two equations, and therefore you should set up two formulas. Setting it up in a table is probably the easiest way to do that. You have water, where you know the specific heat, you know the mass, and I just rearranged the terms a little bit, and you know the two temperatures. You know the final temperature, 29.7, minus the initial temperature, 21.4. So our change in temperature is 8.3 degrees. In other words, water went up by 8.3 degrees centigrade. However, we don't know how much heat the water absorbed. Well, it's easy to calculate from this. We can just multiply this through and figure out that heat. Now we have the second equation for the metal. We don't know the specific heat of the metal. We do know its mass. We do know its initial temperature, 96.5. But look what we picked for the final temperature. The same final temperature as water. In other words, if you put a chunk of hot metal in cold water, eventually they'll both come to the same temperature. So if I tell you the temperature for the water at the end, that's the temperature for the metal at the end too. And you'll notice the metal has a final temperature that's lower than the initial temperature. Therefore, our change in temperature is negative. And that'll mean our heat transfer is negative. But that makes sense. The metal is losing heat, so it's negative. The water is gaining heat, it's positive. Now, the third thing we need to know, besides these two equations, is the fact that the heat that the water absorbs is exactly equal to the negative version of, it's the positive version of the negative heat that the metal lost. So the two Q's are equal to each other except for their sign. The metal's heat is negative, the water's heat is positive. So if we solve for the water's heat first, we get a little over 4,000 joules. So we now know that's how much heat the metal had released, but it's a negative version. So we now know the Q sub metal. We plug that in, and now the only thing we're missing is the specific heat of the metal. We plug those numbers in, and we get the specific heat of the metal is 0.46 joules per degree gram. Remember, specific heat has to have a energy on the top and grams and degrees on the bottom. In this case, it's joules per degree gram or joules per gram degree. These other problems are here for your practice purposes. These are either single equation problems, like these two shown here. And I'll toggle through. You can stop this earlier and go through them yourself, or you can look at the PowerPoint presentation. Here are two more problems. You'll notice in the top problem, you're asked for the final temperature. So you'll have to solve for the change in temperature first, and then solve for the final temperature. And you can look through these to see how to do that. The last equation is looking for the initial temperature. So first you solve for the change in temperature, and then you solve for the initial, knowing the final temperature. And you plug that in. So these are all single equation ones where you're solving for one variable. Here is another lab example. So you have to set up your table just like before, and I'll leave this to you to do on your own because it's very similar to the other example we already did. And you can pause here and go through the problem. I'll just toggle through. And we've got one more that's the same type. You can pause here. And in some of these cases, the metal is releasing heat to the water, and some the water is releasing heat to the metal. And we'll stop here, and good luck.